Batch normalization is another technique used in neural networks to improve their performance and fight overfitting. To prevent the saturation phenomenon, you may want each output of each layer to have roughly the same mean and variance. To prevent this output from getting too large or too small, in order to avoid saturation areas, think about the sigmoid for example, you can try to decorrelate the outputs of each neuron in a given layer so that the next layer takes uncorrelated variables as input, thus leading to linear combination of the same order if the weights are of the same order. But decorrelating variables is a difficult task in neural networks, since you would need to compute the correlation matrix for all layer outputs. Indeed, you do not just want the input variable to be decorrelated, you want decorrelation between all outputs of any layer in the networks. Since computing correlation matrix is costly in high dimensions, decorrelating outputs in all layers is often unfeasible. We are going to use batch normalization instead, which corresponds to normalizing each output of a given layer. Instead of achieving decorrelation, we just want the marginal, each output, to be centered with variance 1 inside each mini-batch. This is done in particular to prevent the network from overfitting to a particular batch of data. Here is the algorithm. So let's start with the first layer of our network. For every unit in the first layer, we let xi be the output of this unit for the ith observation. We compute the mean output mu b and the variance output sigma square b on the current mini-batch. Then we compute the renormalization xi hat for each data, in which we subtract the mean and divide by the square root of the variance plus epsilon, where epsilon is simply a numeric constant which ensures the numerical stability of the division. Then we compute the final output of the batch normalization layer for this neuron, which is yi equal to gamma xi hat plus beta. Gamma and beta are parameters of the batch normalization layer that are going to be learned during backpropagation. This computation was about one neuron, but the other neurons of the same layer are treated in the same way. The output of the batch normalization layer, the values of y's, are then fed into the next layer. Following the same procedure, you can apply any number of batch normalization layer inside the network and you obtain a set of parameters gamma k, beta k to tune, which is done during the usual updating step of the optimization algorithm, since backpropagation allows you to compute the partial derivative of the loss with respect to these extra parameters. During test time, there is a small problem since you do not have access to mu b and sigma b. Indeed, you may want to compute the prediction for one observation, and in this case, sigma b would be equal to 0. To circumvent this problem, which is being able to estimate the variance sigma b square, we compute the average of mu b over many training batches, and we do the same for the variance. This is 0.4 here. At test time, you use these values to compute the output of the batch normalization layer. You may question the relevance of normalizing the output x and then multiplying it by the coefficients gamma and beta. We are going to initialize gamma to 1 and beta to 0 so that at the initialization, the outputs of the batch normalization layer are normalized. We then authorize the network to tune these parameters to improve the prediction. Here we believe that normalizing the outputs helps the network to train. It provides a warm start for the network. Thus, we use the fact that a good default choice for gamma and beta is respectively 1 and 0 and hope that, based on these initial values, the network may learn better parameters.